Hello everyone. So, we are again back to the course Heat Exchangers Fundamentals and Design Analysis. Now, if you recall, we have given some introduction, and after that we have tried to have an overview of different type of heat exchangers we are having, and you should appreciate that this is a very wide variety. And in that variety, we have got different classification of heat exchangers, and one of the classification is based on the compactness of the heat exchangers. So, heat exchangers can be divided into two groups, compact heat exchangers and non-compact heat exchangers, based on surface area per unit volume of the heat exchanger. Some details I will or any of the instructors will try to provide as the course proceeds, but this is one of the important classification of heat exchangers. And then, we have also seen that the compactness or the threshold of compactness based on some magnitude of amount of surface area per unit volume of the heat exchanger, that varies whether depending on whether our fluid is a gas or a liquid. What we will do? We will explain some principles of augmentation of heat transfer, and then some typical method of getting compact heat exchanger design and analysis, that is getting some sort of compactness in the heat exchanger with the use of extended surfaces or fins, that we will try to describe in few lectures to come. So, today is the beginning, this lecture is the beginning of that. At the beginning, we like to have an overview of what are the different methods of augmentation of heat transfer. So, before that, let us see what are the desirable features of a good heat exchanger. There are number of points. I do not claim that the points I have mentioned here are kind of exhaustive. So, there could be some other attributes or some other quality, but definitely I have jotted down the most important features which we expect from a good heat exchanger design, like high heat duty. Heat exchanger should have a high heat duty. Of course, it should be qualified that for a given volume or given envelope shape of a heat exchanger, it should have the highest heat duty as far as possible, as far as practicable by the technology available. Then low temperature difference. Basically, we are transferring heat between two streams, and the potential for this transfer process is the temperature difference of the two streams. So, it is obvious that more the temperature difference, more will be the heat transfer, but can we have very large heat transfer with a small temperature difference? So, that is the goal, or that is the desirable feature of the heat exchanger. Then compact size and less weight. Compact size and less weight, it is I mean always it is some goal of any engineering design, because you see that we have got restriction of space, we have got cost of material, we have also the restriction for weight, particularly if a system is a mobile system, we have got different implication if we go overweight. So, for all these things, compactness is one point. Apart from that, what we want to have? We want to have less pressure drop. Generally, what happens? Pressure drop depends on many parameters. One of the most important parameter is the fluid velocity, but along with this, if the fluid within the heat exchanger has to pass a very long pathway, then there will be high pressure drop. So, we have to also see that the pressure drop should be low, and up to this I have given different color, because at the beginning or somewhere in the course we are going on mentioning that we will look into the thermal hydraulic aspects of heat exchanger. may not be the other design aspects, other manufacturability aspect. So, these 4 points are very important for us. But on totality, for an engineer who is designing heat exchanger or working on heat exchanger, see, other points are also important. These points could be less prone to fouling, ease of cleaning and maintenance, that is the serviceability of the heat exchanger, and over and above, for any engineering system, for any man-made system, cost is a prime factor. So, whatever we design, our economy should allow that. So, we should have the lowest cost of the heat exchanger. So, 4 points, see 4 point at mentioned at the top, those are very important as far as the thermal hydraulics of heat exchanger is concerned. So, we have to have high heat duty. We desire to have a low temperature difference between the two streams. We obviously wants to have our heat exchanger to be small and less weight, lightweight, and there should be less pressure drop. So, with these 4 points, let us proceed. So, how we can have it? So, basically we can have these 4 points we have told. Out of that, at least the first 3 points, that means high heat duty, low temperature difference and lesser volume or weight of the heat exchanger, that we can have with a very good or very effective way of heat transfer. And we can also argue that if our heat transfer process is very effective, very good, very efficient, then also we will end up with a design where there will not be excessive pressure drop. So, this comes that whatever normal heat transfer is there, we will try to enhance the rate of heat transfer or augment the rate of heat transfer. This is very important, particularly for the heat exchanger industry and also for other places like electronic component cooling, heat sink design, etc. So, augmentation of heat transfer or enhancement of heat transfer is a very special topic and very useful branch of heat transfer in general. Now, in heat exchanger, normally there are 3 modes of heat transfer: conduction, convection and radiation. But as we are transferring heat in most of the cases from a moving fluid to another fluid stream, convection is the main mechanism of heat transfer, and if we can improve the improve convective heat transfer, then we have improved the heat transfer process. So, first I have written augmentation of heat transfer primarily gives saving of material and energy. Whenever we are talking about advanced heat exchanger, compact heat exchanger, obviously one of the main goal is to reduce the size of the heat exchanger. So, the basic energy balance equation, what we can get, the basic energy balance equation what we can get is that let me highlight it. So, this is the basic energy balance equation for convective heat transfer. Q dot is equal to H A T W minus T F. I have shown it with the help of an illustration which is very common to you. This is some sort of a solid surface on which there is a flow of liquid flow of a fluid, and the solid surface is kept at a surface temperature, let us say, that is equal to T wall, and the fluid is flowing over the surface with a velocity T infinity. So, on the solid surface there will be a velocity gradient due to formation of boundary layer, there will be a temperature gradient due to the formation of thermal boundary layer. And heat transfer will depend on the difference, that T infinity, that is the temperature of the fluid outside the thermal boundary layer, and T w is the temperature of the fluid, T w is the temperature of the fluid on the surface. So, Q will be H A T w minus T f. So, you see in this equation we want to maximize, let us say we want to maximize Q, our TW and TF are fixed, then we have got these two quantities H A. H is the heat transfer coefficient and A is the surface area. So, when we are going for augmentation of heat transfer, particularly we are having single phase fluid and the mode of heat transfer is convection, convection from the between the wall and the fluid stream, then we have to concentrate on H A either separately or as a combination. So, augmentation technique aim at modifying H A by improving H or A. If we go to the next slide, so before that let me tell you H A, let me go back to our previous slide and sorry, let me go back to the previous slide. It is going in the opposite. Let me see what is happening. Oh, it is going back. Sorry for the okay. Okay. Sorry for this small problem. So, what we see that here we are having H A, A is the area and H is the heat transfer coefficient. So, H depends on various things, that depends on the of course, on the fluid property, fluid velocity and the surface geometry, particularly the features which are available on the surface. So, there are many ways of increasing or there are many ways of enhancing H, and there are ways of enhancing area or A also. There are some ways by which the combination can be improved, that means both H and A can be improved. So, we will see some of them. So, techniques of heat transfer augmentation, a class of technique that those are known as passive techniques. As the name suggests, in this technique we do not need any auxiliary power. We have some design modification, and with the design modification we can have the heat transfer augmentation. Like we can have treated surface, there is some sort of a surface treatment, so that there are micro scale features on the surface. In case of phase change heat transfer, there could be the chemical features of the surface that could also be different. Surface can be roughened, there could be extended surface, while rough surface or the treated surface gives features of very small scale. Extended surfaces or fins, which are as they are known very popularly. So, these are large features present on the surface and that increases the surface area. Then inserts and swivel devices, which can be put in the inside the flow passage, then additives for liquids and gases, and then rib roughened surface. Okay. So, some of them let us see, we will have a look and we will have some appreciation of some of these devices. Before that, let us see this small illustration. Here we have a corrugated surface, which is I have shown an exaggerated view. So, in this we have got this is the direction sorry. again we went forward. So, in this the features I have shown in an exaggerated manner. So, basically there is not much change on the surface area, but due to the placement of this feature there will be change in the velocity field very near the wall, and we will have some increase in h. So, this is where we are increasing h without increasing the area. Here I have shown one extended surface or fin. So, basically it is increasing the surface area, and here there are offset strip fin. So, it is like this, that small fins are placed in the staggered manner on the flow field or in the path of the flow. So, on the fin there will be boundary layer development, but as the fins are small, the boundary layer cannot develop infinitely and cannot reduce the rate of heat transfer. Backside of the fin there will be vortex formation. So, boundary layer will get some sort of an obstacle for further growth. Heat transfer coefficient will start increasing, and at the same time the small fins they are giving an increase in area. I would like to show you some other example as we proceed. Here we have shown techniques for heat transfer augmentation, basically passive augmentation. The first one you see, this is a tube, but the tube surface has been given some sort of a shape, so that the boundary layer is disturbed and gives more heat transfer. In the second one, that is B B, so there are some sort of microfin over the tube surface. In C, there are fin inside the tube, different kind of fins, small fins inside the tube, and these fins, as they are small, they are not only and particularly when they are inside. So, they are not only increasing the surface, they are also giving a rise in the heat transfer. D, there is again on the tube geometry there are some variation. So, that will give some enhancement in heat transfer. Below what we can see, that here we have got some sort of a tape insert here in this diagram. We have got a tape insert inside the tube. So, the heat transfer will increase. Here the last one, here we have got some sort of wire insert inside the tube, which will give good mixing and better heat transfer. And then active techniques. Active techniques means that we have to spend some energy more than what we are spending for the fluid flow. Additionally, we have to spend certain amount of energy. So, there could be mechanical aids like scrapping or agitation. In case of many chemical reactors where heat exchanger is also integrated with the reactor, we have got these agitators. For viscous fluid, we have got scrapped surface heat exchanger, as I have mentioned in some of the lectures earlier. Then there could be surface vibration. So, all these things, two goals are there. Either we are trying to disturb the boundary layer, which gives the main resistance to heat transfer and which forms on the wall. So, either we are trying to disturb that, or we are trying to give a good mixing to the bulk of the fluid. So, by passive technique also we try to do that, and by active technique also we try to do that. By passive technique we try to do another thing more, that we sometimes try to provide more surface area. So, surface vibration is one thing. As surface vibration can give good amount of mixing, then similarly fluid pulsation can give good amount of mixing. Then electrostatic field, this is very unique. So, if there is a dielectric fluid, then we can provide some sort of a electrostatic field, and with the help of electrostatic field we can have a good kind of transport of the particles, and that will give higher heat transfer. Again, these are particles which are microscale particle fluid, the molecules of the fluid, when they have a movement due to the electrostatic field. So, obviously, at the microscopic level they produce some sort of agitation. When we are providing some sort of mixer, insert, etc., that is providing agitation at the macroscopic level, but this is at the microscopic level. Now, many cases we go for hybrid technique and compound enhancement. Two techniques are combined together. Let us say two passive techniques can be combined, one passive and one active technique can be combined, and two active techniques can be combined. Let me give one example, and with this example we can probably end our discussion. So, here this is kind of a, think of a fin tube heat exchanger. So, first what one can think that tubes are used for circulating some sort of a liquid, and this liquid has to be either cooled or heated. So, what we can provide that on the outer surface of the tubes we can circulate some amount of gas, but gas side heat transfer is small. So, what we can do to improve the gas side heat transfer, we can provide extended surface or fin which is shown by this strip. So, now you can understand the arrangement. These are showing the tube cross section through which your some liquid is passing. Surrounding the tube we have got plate, thin plate, which will act as an extended surface or fin. This will give augmentation of heat transfer, and this is a passive augmentation of heat transfer. So, this is the basic design, and on this basic design what I have done here, we have provided rectangular winglet for alternate tubes. So, when the fluid flow will take place, so there some sort of a vortex will be created behind this winglet. So, fluid flow is taking from this side, and behind this winglet we will have some sort of a vortex which will give higher heat transfer due to the change in the heat transfer coefficient. So, one passive technique is increasing the surface area, the another passive technique is increasing the heat transfer coefficient. Two different passive technique we have used, and with that we are getting a much larger heat transfer. So, so this is one way how we can combine two different augmentation techniques together. Let me give some sort of concluding note for whatever we have summary and concluding note for whatever we have discussed. Though we are calling passive technique does not need any kind of auxiliary power, but most of the passive technique will have increase in pumping power. We have not to provide any kind of auxiliary device, auxiliary arrangement for power supply, new power supply obviously, but the fluid pumping power that generally increases. So, this is one point people have to be careful when we are selecting a particular augmentation technique. That is one thing. Second thing, generally augmentation techniques, when you adopt augmentation technique, so you have increase in initial cost, increase in weight and volume of the heat exchanger or heat transfer device. So, this is also one point which needs to be considered. Here again I like to mention one thing, that first what I have informed, that either we have to use auxiliary power, or if we are using passive technique, then what we have to do, that we have to go for excess of pressure drop, that pressure drop penalty we have to admit. So, if we are admitting excess pressure drop, then what is happening? We are again spending some more amount of power. So, here some reference from thermodynamics may be drawn, that we want to enhance the rate of heat transfer. For that we have to spend some amount of power. When we are trying to have more heat transfer, we are dealing with a low grade energy, but when we are spending pumping power, we are dealing with a high grade energy. So, this is like this, it is like this, that we have to be very careful. Our heat transfer should be much more, or from the energy point of view, magnitude of energy point of view, our rate of heat transfer enhancement should be much more compared to the amount of pressure work we are spending for the change in design. So, this is one point you have to be very careful. Performance evaluation of augmented surfaces. So, first thing what we can see, that reduction of size keeping delta T m and q constant. So, this could be one way, that suppose we are keeping q and delta T m constant, that is the total amount of heat transfer, and the mean temperature difference between the two fluid stream we are keeping constant. So, whether we can reduce the size of the heat exchanger by the augmentation techniques adopted. So, this could be one. Then the second one could be that reduction of delta T m keeping q and size constant for heat exchanger. So, let us say that earlier my process I have designed with a large temperature difference between the two fluid streams. Now, what I will do? I will have the same amount of heat transfer, I will have the same area or rather same volume of the heat exchanger, but I will I have gone for augmentation technique. So, I will have lesser amount of delta T m. So, this could be also one goal, and it may be possible, not in all cases, that by all this process, as I have made my heat exchanger very small, as I have made my transfer processes very efficient, that I may achieve this with a lesser pressure drop. So, this may happen, this may not happen. So, it may be possible to reduce delta P keeping Q constant. However, compact heat exchanger generally aim at a reduction in size. So, this is one thing we have to remember, that whenever we are talking about compact heat exchanger, generally we mean that there is a reduction in size. Let us quickly see that augmentation of heat transfer during phase change, boiling and condensation. So, this is initially I have discussed what we should do for single phase flow, but when there is a phase change, the principles are completely different. In case of boiling, generally what we try to do, that some sort of a degree of superheat is needed between the solid surface and the fluid for initiate nucleation. So, our surface design should be such that this delta superheat is reduced. That means, basically we are reducing the effective temperature difference between the surface and the fluid. The generation of more nucleation site, we need to have more evaporation or more vapor formation. So, from many more places there should be formation of vapor. Then increase in the range of nucleate boiling. Actually, I will touch upon boiling, but this is as we are discussing augmentation. So, this point I want to tell, that nucleate boiling is a very high rate of heat transfer and safe method of heat transfer during boiling. So, we want to increase its range, temperature range basically, and we want to increase the magnitude of critical heat flux. Critical heat flux is again one heat flux. Probably most of you know it, because as the prerequisite of this course, probably all of you have attended heat transfer course, and there you are familiar with different regimes of boiling. So, maximum heat flux that we can allow in many industrial equipment is the critical heat flux. Then if there is any excessive vapor formation, so there should be immediate removal of vapor. Condensation, in condensation if we can have dropwise condensation, that is good, and quick removal of condensate film if we are having film wise condensation. So, these are the method of augmentation in boiling and condensation. Probably we will revisit and see closely some of them when we will learn about the phase change heat exchangers. So, with this I like to come to an end of this lecture, and let us see some augmentation technique in details in our next lecture. Thank you.